Rutgers University. We'll be speaking about congruent subgroups of lattices and rank 2 Kac-Moody groups over finite fields.
My name is Abib and I am a visiting scholar from Pakistan, visiting Professor Kac-Moody at Rutgers University. First of all, I would like to thanks for providing me this opportunity to give a seminar in New York algebra property. I also would like to pay my gratitude to Professor Kac-Moody who let me to work with her. Today, I will talk about congruent subgroups of lattices in rank 2 Kac-Moody groups. In this talk, we will see an analogy of the Kac-Moody groups with the Lie groups. By using the group action of rank 2 Kac-Moody groups on its tree, we obtain graph of group presentation for certain lattice subgroups of rank 2 Kac-Moody group. We also define the notion of congruent subgroups of rank 2 Kac-Moody groups over finite field, and I will describe the structure theorem which we have obtained. My talk will proceed in the following steps. First of all, I will give the theorem, and then there will be a brief introduction of Kac-Moody groups. After that, there will be the graph of group presentation for the lattice subgroups of rank 2 Kac-Moody groups, and then I will define the congruent subgroups of these lattice subgroups. After that, there will be the graph of group presentation for these lattice subgroups, and finally, I will give some other direction in which this work can be extended. JP Serre constructed an amalgamated sum of the group of invertible matrices with entries from polynomial ring over one indeterminate T and with coefficient from finite field K. He also described the amalgamated product of SL2 KT. In the same book, he gave an amalgamated form of for SL2KT, where gamma n is the group consisting the matrices of determinant 1 and Bk is the union of these two subgroups, intersections. To obtain these amalgams, he used a technique based on group action on its tree. And to obtain these results, he used the main theorem, which is main theorem of Bas-Serre theory, that when a group G acts on its tree without inversion, then the group is isomorphic to the fundamental group of the graph of group, and the tree is isomorphic to the universal cover of the graph of groups. We will use the same theorem to obtain the results for our lattice subgroups, to obtain the graph of group presentation for our lattice subgroups, where which are P1 minus, B minus, and U minus, where U minus is the group generated by the negative real two group, and B minus is the product of H and U. Where H is isomorphic to the direct product of multiplicative group of finite field, and P1 minus is the standard parabolic subgroup for the negative Bn pair of the G. I will give some basic definitions which will be used during the talk. Let G be a Kac-Moody algebra. This is the Kac-Moody algebra is most natural generalization of finite dimensional simple Lie algebra to infinite dimension, and we have root system for this Lie algebra, and while group which is generated by here y are simple roots, and W is generated by simple root reflections. Where alpha ij is the are the entries from the generalized Cartan matrix, and the while group is generated by these simple root reflection. In our case, while group is generated by W1 and W2, which is isomorphic to dihedral, infinite dihedral group. We have real roots which are which we obtain when Wx on simple roots, and these real roots can be described along the branches of hyperbola like this. And we obtain a disjoint partition of the real roots into two sets which lie along the upper branch and along the lower branch. We have this basic data to proceed, and it has been a difficult question to associate a Kac-Moody group with Kac-Moody algebra. Many constructions have been given by various mathematicians. The main thing which they use in their construction is Tate's functor. Tate's, in 1987, Tate's associated a group functor over the category of commutative rings, such that for every generalized Cartan matrix A and for every commutative ring R, there exists a group functor associated with this A and R. Professor Carbon and Professor Garland, in their paper Existence of Lattices and Kac-Moody Groups over Finite Field, gave the interpretation of this its functor by using the representation theory of Kac-Moody algebra. And for finite field, we have this group, Kac-Moody group, generated by these symbols, which are actually linear automorphism of K form of highest weight vector, irreducible highest weight module corresponding to dominant integral weight alpha, lambda. So we have now we have a group G which is generated by these linear transformations, linear isomorphisms, and these are the commutation relations defined in the group, that if alpha beta both belongs to the same branch, then they will commute. Then the symbols related with those roots will commute with each other. In the same paper, Professor Kac-Moody and Professor Galland showed that the group Kac-Moody groups have twin BN pairs, positive and negative, where B plus is the semi-product of B minus is the semi-product of H and U minus, and N is generated by omega and H, where omega is generated by where U will be from a multiplicative group of finite field, and there are 4 standard parabolic subgroups, each pair associated with positive and negative BN pair associated with the group G. There are two buildings associated with this group G corresponding to the positive and negative BN pair of the group G. In rank 2 case, we have this building, a homogeneous bipartite tree whose vertices are the coset of standard parabolic subgroups in G, and whose edges are cosets of minimal parabolic subgroup in G, and this coset space is just for keep the orientation. And for the field of 2 elements, we will have tree associated with this group like this. For the field of element 2, we will have tree associated with Kac-Moody group of this form, and this will be the standard apartment, which is infinite ray. Here it is for the field, for any finite field, and this can be seen here that this is the standard apartment. Now we define the cuspided root subgroups along the branch, upper branch and lower branch for the support of real roots for the Kac-Moody group. These are finite subgroups which are the product of the symbols corresponding to the roots